The given code snippet consists of import statements in Python, each of which is used to bring in external Python libraries or modules that are necessary for the functionality of the subsequent code. The pandas library is imported with the alias PD, which is used for data manipulation and analysis, particularly for working with tabular data and data frames. The NumPy library is imported with the alias NP, which is handy for numerical computations and working with arrays. The pathlib module's path class is imported for object-oriented file system paths, making it simpler to work with file paths. The hplot.pandas is imported, which is an extension for the pandas library, provided by HoloViz. This enables creating interactive plots using hvplot directly on dataframe objects. Matplotlib.pyplot is imported with the alias plt, which is a plotting library used for creating static, interactive, and animated visualizations in Python. The SEM module from Scikit-learn scikit-learn library is imported for performing support vector machine algorithm tasks, which is a machine learning tool for classification and regression. The standard scaler is a pre-processing module from Scikit-learn that is used to standardize features by removing the mean and scaling to unit variance. The dateOffset class is imported from pandas.series.offsets, which is used for date calculations in time series data. Lastly, the classification_report function from Scikit-learn.metrics is imported to construct a text report showing the main classification metrics, which is helpful in evaluating the performance of classification algorithms. This specific code does not execute any functional operations by itself. Instead, it sets up the working environment by ensuring all necessary tools and methods are available for data loading, manipulation, visualization, pre-processing, modeling, and evaluation that will follow in the rest of the program or script. This code snippet is designed to import a dataset of open high-low close volume, OCHL-CV, stock market information into a Python environment using the pandas library. The dataset is assumed to be in CSV format and is located at the given relative file path, /resources/emerging_markets_olg.csv. The code instructs pandas to read the CSV file, set the date column as the index for the data, infer the format of the date strings, and parse the date strings into Python datetime objects. This is achieved using the pd_read_CSV function from pandas, with appropriate parameters for handling dates. After importing, the code reviews the data frame by displaying the first few rows using the head method, which provides a quick snapshot of the dataset structure and content. The provided code is designed to operate on a data frame named olk_df, which likely contains open high-low close volume, OCHL-CV, data typically used in financial markets analysis. The code accomplishes several tasks. 1. It begins by creating a new data frame signals_df that consists only of the close column from the original olk_df, effectively filtering out all other columns. 2. Next, the code computes the percentage change of the close price, which represents the returns from one close price to the next. This percentage change is then assigned to a new column in signals_df, named actual returns. 3. The code proceeds to clean the data by removing any rows with nan, not a number, values, which are most likely to appear after the percentage change calculation, since the very first close price does not have a preceding price to calculate a return from. 4. Finally, the first 5 and last 5 rows of the resulting signals_df data frame are displayed, typically for a quick visual check to ensure that the data processing steps have been carried out correctly. The display functions are likely a part of an interactive environment, such as Jupyter Notebook, where the output would be shown inline. The purpose of this code is to calculate and add 2 new columns to an existing data frame, signals_df, that contains simple moving averages, SMA, of closing prices. A simple moving average is a technical indicator used in financial analysis to smooth out price action by calculating the average price over a specific number of periods. The code determines 2 different periods for calculating these moving averages: a short window, short_window, set to 4 periods, and a long window, long_window, set to 100 periods. It then calculates the SMA for the shorter period and assigns this to the SMA_fast column, which represents the fast moving average of the close prices over the last 4 periods. The SMA for the longer period is assigned to the SMA_slow column, which represents the slow moving average of the close prices over the last 100 periods. The rolling mean calculations are applied to the close column of signals_df, presumably where the closing price data of a security is stored. After calculating the SMAs, the code drops rows with missing values caused by the rolling function, as there won't be enough data points to calculate SMAs for the initial periods equal to the size of the rolling windows -1. Finally, the code prints the first and last few rows of the modified data frame by calling display signals_df.head and display signals_df.tail, which shows the starting and ending values of the dataset with the newly calculated simple moving averages for both short and long windows. This can be helpful for reviewing and verifying the calculated moving averages. This code is intended to manipulate a financial data frame named signals_df that contains a column of actual returns. The code first adds a new column to signals_df called signal and initializes all the values in this column to 0.0, representing a neutral signal. It then sets up a long signal, represented by the value 1. for rows where actual returns are greater than or equal to 0, indicating a buy signal for the associated stock. Conversely, it establishes a short signal, represented by the value -1, for rows where actual returns are less than 0, indicating a sell signal. The code finally uses two display functions to show the first few and the last few rows of the updated signals_df data frame, which helps in reviewing the changes done to the signals based on the actual returns. The code snippet is performing an operation using the pandas library on a data frame named signals_df. It selects a column from this data frame called signal and then applies the value_counts method to that column. The purpose is to count the occurrence of each unique value in the signal column. The value_counts method will return a series containing counts of unique values in descending order, so that the first element is the most frequently occurring element. It indexes the series with the unique values from the signal column. This can be useful for understanding the distribution of different signals within the dataset or for further analysis like filtering or data manipulation based on these frequencies. The purpose of this code is to calculate the investment strategy returns based on actual returns and trading signals, and then to add these calculated strategy returns to an existing data frame called signals_df. The calculation of strategy returns is performed by multiplying two columns in signals_df, one that contains the actual returns of an asset, actual returns, and another that contains trading signals, signal. The trading signals are shifted forward by one period using the shift method to align them with the period for which they will be applied. This typically represents the idea that a trading signal would result in action in the following period, not the current one. Once the strategy returns have been calculated, they are stored in a new column of signals_df called strategy returns. After updating the data frame with the new information, the code then uses the display function twice to show the user the first few rows, via head, and the last few rows, via tail, of the updated signals_df. This allows the user to quickly review the data frame and confirm that the strategy returns have been appended correctly. This line of code is used for plotting the cumulative product of the strategy returns from a data frame named signals_df after incrementing it by 1. The purpose is to visualize the cumulative performance of a trading or investment strategy over time. The .comprod function calculates the cumulative product of the strategy returns as if someone were reinvesting their returns back into the strategy. By adding 1 to the returns, it accounts for the initial value. The .plot function then generates a line graph of these cumulative returns, which allows the user to easily see how the strategy's performance has grown or shrunk over the time period represented in the signals_df data frame. This visualization is useful for assessing the effectiveness and the overall trend of the strategy's returns. The provided code snippet is designed to prepare a features data frame called X to be used in a machine learning model or data analysis context. Specifically, it is taking two columns SMA_fast and SMA_slow from an existing data frame named signals_df and assigns a copy of them to a new data frame called X. Prior to the assignment, the .shift method is applied to both columns, which moves their data down by one row, effectively introducing a lag of one time period to the values. This is typically done to avoid look-ahead bias in time series analysis where the model or analysis should only use information available up to that point in time. Once shifted, any rows containing NaN values, which are introduced by the shift operation to the first row, are removed using the .dropNum method, ensuring that X does not contain any missing values. The final line, x.head, is not part of the assignment to X. Instead, it is likely intended for display purposes and would output the first few rows of the X data frame when executed, allowing the user to review the initial portion of the prepared dataset. This piece of code is designed to extract a column named signal from a data frame called signals_df and assign it to a variable called y. After the assignment, it performs two operations to inspect the data in y. The first operation, y.head 50, displays the first 50 values of the signal column to give a quick overview of the data at the beginning of the series. The second operation, y.value_counts, tallies the frequency of each unique value within the signal column, thus providing insights into the distribution of data within that column. These operations are typically used for a preliminary examination of the data during the data analysis process. The provided code snippet is written in Python and is used to determine the earliest date in a dataset, which is assumed to be a time series, and printed out. This earliest date is considered the start of the training period for some kind of time series analysis or predictive modeling task. Firstly, the code presumes the existence of an object X, which is likely a pandas data frame or series object that has a datetime index. The method x.index.min is called to compute the minimum date in the index of X, effectively finding the earliest timestamp contained within it. The result of this computation is then stored in the variable training_begin. Lastly, the code prints out the value of training_begin, which should display the earliest, minimum, date from the dataset index on the screen. This information can be important for understanding the time frame covered by the training data in a chronological dataset. This Python code snippet is designed to set a variable named training_in to a date that represents the end period for a set of training data. It does this by selecting the minimum date from an index, presumably a pandas datetime index, associated with the dataset X, and then adding an offset of 3 months to this minimum date. The date offset, months equals 3, part of the code specifically creates a time delta that represents a 3-month period. The computed training_end date is then printed out, which informs the user of the cutoff date for the training data. The snippet is likely part of a larger data preparation process where historical data is split into training and testing periods for the purposes of training a predictive model. This code snippet is meant for generating training datasets from larger datasets denoted by X and Y. In machine learning, models are usually trained on a subset of the data, referred to as the training set. The X data frame contains feature data, and Y contains the labels or target variable that the model aims to predict. The code selects a subset from each of the original X and Y data frames using a time slicing method. It uses training_begin and training_end as index markers to slice the data frame. These variables are assumed to define the start and end points for the training dataset, based on either the index value or a timestamp within the data frame indices. After creating X_train from X and Y_train from Y, it then takes a preview of the first few entries in the X_train data frame by calling the head method, which by default shows the first 5 rows. This is a common practice to verify that the data has been sliced correctly before moving on to the actual training of the model. The purpose of this code is to generate testing datasets for some machine learning or data analysis task. Specifically, 2 pandas data frames X_test and Y_test are being created. These data frames are intended to be used as the input features, X_test, and the target variable, Y_test, for model validation or assessment of its performance. X and Y appear to be pre-existing data frames that presumably contain the features and target variable for the complete dataset, including both the training and testing data. The code uses a training_end variable, which seems to hold the timestamp indicating the end of the training data period. The code slices both X and Y data frames to create the test datasets. It selects all the rows from the timestamp just after training_end, as increment by 1 hour using the date offset, hours equals 1, and up to the last entry. The lock method is used for this purpose, which allows selection by label, in this case, the timestamp. After creating X_test and Y_test, the .head method is called on X_test to display the first few rows of the data frame. This is often done to verify the content and structure of the data, ensuring that the correct subset has been selected for testing. The purpose of this code is to standardize the features in the data sets used for training and testing in a machine learning application. Initially, it creates an instance of the standard scalar class from a machine learning library, most likely scikit-learn. This scalar is then fitted to the training data X_train, which calculates the mean and standard deviation for each feature in the training set. After fitting, the scalar is used to transform both the training data X_train and the testing data X_test, resulting in X_train_scaled and X_test_scaled. These scaled data sets have transformed features where each feature in the training set has a mean of 0 and a standard deviation of 1. The testing data is scaled using the parameters from the training data to ensure consistency. Standardizing features is a common pre-processing step to improve the performance of many machine learning algorithms by giving equal importance to all features and helping algorithms to converge more quickly. This Python code snippet is using the support vector machine, SVM, algorithm for classification by creating an instance of the SVC, support vector classifier, model from the scikit-learn library. First, it instantiates the SVC model and assigns it to the variable SVM_model. Then, it trains the model using a scaled version of the training data, both features, X_train_scaled, and target values, Y_train, by calling the fit method on SVM_model. Once the model is trained, it generates predictions using scaled testing features, X_test_scaled, by calling the predict method, storing the predictions in SVM_pred. Lastly, the code provides a quick review of the first 100 predicted values from the test set by displaying them. The code does not contain the actual implementation for data pre-processing, scaling, or the definitions of X_train_scaled, Y_train, and X_test_scaled, as it assumes these have been created elsewhere in the surrounding program. This code snippet is used to evaluate the performance of a model that has been used for a classification task. It does this by comparing the true labels of the data, Y_test, with the predictions made by the model, SVM_pred, using a function called classification_report from a machine learning library, likely scikit-learn. The classification_report function generates a text report showing the main classification metrics including precision, recall, F1, score for each class, and the averages of those metrics. The report provides insights into how well the model is performing, considering both the ability of the model to correctly predict each class precision and the completeness of the predictions recall. After generating this report, it is then printed out to the console, allowing the user to review the model's performance metrics. This step is typically used for giving a detailed assessment of a model's accuracy and effectiveness in a classification problem. The given code snippet is used to create and manipulate a pandas data frame named predictions_df. This data frame is initiated as empty with the index based on another data frame x_test. Then, the code adds several columns to the predictions_df. The first column is predicted, which contains predictions from a variable svm_pred. It's implied that these predictions might be the result of a support vector machine model. Subsequently, the column actual returns is added, containing data from a column in yet another data frame referred to as signals_df. This suggests that the data frame may pertain to financial data where actual returns could signify the returns of a financial asset. The third column strategy returns is calculated by multiplying the actual returns by the predicted values, which might indicate the performance of a trading strategy if the predictions are interpreted as signals, e.g., 1 for buy, -1 for sell. Finally, the code uses the display function to show the first and last few rows of the predictions_df, giving an overview of the data frame contents at both the beginning and end of the dataset. This code snippet is intended for visualizing financial data by plotting the cumulative product of actual returns versus strategy returns over time, presumably from an investment strategy or model's predictions. The predictions_df is a data frame that contains two columns, actual returns and strategy returns. These columns hold the return values of an actual investment and a proposed strategy, respectively. The code performs a cumulative product operation on these columns by first adding 1 to each value to address the rate of return calculation, and then calculating the cumulative product using the comprod method. This operation effectively illustrates the compounded value of returns over time, as experienced by an actual investment compared to the investment strategy. Finally, the resulting data frame, consisting of the cumulative product of the actual and strategy returns, is passed to the plot function to create a line plot that visually compares how both the actual and strategy-based investments would have grown over time. This visualization can be useful for analyzing the performance of a given investment strategy against real market outcomes. This code performs two main functions. First, it imports the logistic regression class from the linear_model module within the scikit-learn, often imported as sklearn, library. This class allows the user to implement logistic regression, a popular statistical method that models the probability of a binary outcome based on one or more predictor variables. After importing the logistic regression class, the code then proceeds to instantiate an object of this class, creating a logistic regression model named log_regress_model. This instance can be used to fit data for binary classification tasks, make predictions, and evaluate the performance of the model on a dataset. Essentially, this code sets up a new logistic regression classifier that is ready to be trained with data. This line of code represents the process of training a logistic regression model using a pre-processed dataset. The variable log_regress_model is assumed to be an instance of a logistic regression model, likely from a machine learning library, such as scikit-learn. The fit method is called on this model with two arguments, x_train_scaled and y_train. x_train_scaled is the feature matrix after scaling, containing the independent variables for the training set. Scaling the data is a common pre-processing step to normalize the range of different features, which can be important for algorithms like logistic regression that are sensitive to feature scaling. Y_train is the target vector for the training set, containing the dependent variable, the outcome or label that the model is trying to predict. Essentially, this code trains the logistic regression model on the given training data, allowing the model to learn a relationship between the features and the target. After executing this line, the log_model variable would hold a trained model that can be used for further predictions or analysis. The purpose of this code is to generate predictions from a trained logistic regression model, log_model, using a scaled testing dataset, x_test_scaled. The model's predict method is applied to the testing dataset to produce the predicted outcomes. The code snippet includes a comment indicating that the testing dataset is being used to generate predictions. After generating the predictions, the code samples and displays the first 100 predicted values from the array pred. This is commonly done to quickly review the model output and check the predicted values for the initial portion of the test data, which can be helpful for initial evaluation or debugging purposes. The provided code snippet is used to evaluate the performance of a classification model by generating a classification report, which includes key metrics such as precision, recall, F1, score, and accuracy. The classification_report function from the sklearn.metrics module is called with two arguments, y_test and pred. Y_test refers to the true labels from the test dataset, while pred contains the predicted labels produced by the model. The report aims to provide insights into how well the model is able to predict each class. After generating the classification report, it is stored in the variable log_model_classification_report. Finally, the code prints out the contents of this variable, displaying the report to the user. This printout would typically show the performance of the model for each class, as well as the overall averages of the mentioned metrics, helping the user to understand the model's strengths and weaknesses. This code snippet is designed to create and manipulate a pandas data frame which serves to compare predictions from a logistic regression model with actual results and calculate the returns of a certain strategy based on those predictions. Firstly, an empty data frame named predictions_df_with_log is created with the same index as x_test, which presumably contains test features for the model. Next, a column named predicted is added to this data frame storing predictions from a logistic regression model, with variable pred presumably containing these predictions. Following that, a column named actual returns is added, which would include actual returns from a data frame signals_df, suggesting that there is a financial context for these calculations, probably a trading algorithm. Subsequently, strategy returns is tabulated by multiplying the actual returns by the predicted values, presumably to model the returns of a trading strategy where the sign of the prediction, buy, sell, or positive/negative, directly affects the outcome. Lastly, the beginning and end of this resulting data frame are displayed, which allows for a quick manual inspection of the process data. The purpose of this code snippet is to generate a plot that compares the cumulative product of actual financial returns with the cumulative product of returns generated by a particular trading strategy. It takes a date frame called predictions_df_with_log and selects two columns, actual returns and strategy returns. The code assumes that the date frame contains the daily log returns of some financial instrument for the actual returns and the returns of a trading strategy for the strategy returns. The cumulative product is calculated by taking 1 plus the selected columns to account for the starting value of an investment, and then applying the cumrod function, which calculates the cumulative product along the data frame's index. This operation effectively simulates the growth of an initial investment over time based on the provided returns. Finally, the plot function is called on the result to create a visual representation, typically a line plot, showing the progression of both the actual returns and the strategy returns over time. This visualization can be useful for comparing the performance of a trading strategy against the performance of the actual returns, allowing for a visual assessment of how well the strategy has performed historically.